All right. Yesterday we discussed E plus E minus to mu plus mu minus scattering, and we already looked at various physically interesting limits, namely high energy limit and low energy limit, and we also discussed the angular dependence. And there was a particularly interesting angular dependence which depended on cosine of the scattering angle theta. And I already announced that we can understand the angular dependence in a little bit more physics terms by angular momentum conservation and spin conservation and spin dependence. And that is what we want to do now. We want to look at the process once again and calculate it to some extent, but with explicit spinors which involve explicitly the scattering angles theta. And we want to do that only in the high energy limit where we did discover this angular dependence. And so we go to the purely massless case today. And here I wrote down already a copy of the spinors for massless spin 1/2 particles, which is a copy of our spinor script. And we can use them now in our calculation and the physics discussion. So the case we are now considering is that the masses of all particles are 0. We will do the exactly massless limit. In that massless limit, there is a new physical phenomenon appearing, namely, there is the concept of helicity, which is the spin in the direction of motion. And the helicity of our electrons and muons can be plus minus 1/2, of course. But in the case of a massless particle, helicity becomes a Lorentz invariant quantity. And that is the special thing about the massless limit. And in the massless limit, helicity becomes equal to the so-called chirality. And chirality is the concept of eigenvalues of the gamma 5 matrix. And let me just indicate that here. All the spinors that you see here on the blackboard, which are massless spinors with helicity eigenstates, they are at the same time eigenspinors of gamma 5. So for example, that spinor here is equal to the right-handed projection operator P right acting on itself. And so the right-handed symbol here of chirality, so that is 1 plus gamma 5 over 2, corresponds to the right-handed helicity here. Here also that spinor for an antiparticle with helicity minus 1/2 is equal to P right times itself. So here there is the kind of awkward situation that right-handed chirality corresponds to left-handed helicity. That is the case for antiparticles, and that is a fact of life. And so on, but all the spinors that you see here are eigenstates of gamma 5, and they have specific relationships with respect to those right-handed and left-handed projectors which involve the gamma 5 matrix. And that is something that one can use also in calculations. So helicity becomes equal to chirality. And is Lorentz invariant. Okay, then we can look at the sketch of the process in the center of mass reference frame, where the E plus E minus collide head-on into some central collision point. And then they have now some helicity, which is equal to chirality. And let us just assume something. Let us start with the initial state electron here to have, for example, that kind of helicity. And of course, the opposite case would behave analogously. So we will only consider that kind of situation. If we assume that to begin with, so let's assume E minus has a helicity minus, plus 1/2. This is supposed to be right-handed. Then the question is, which helicity must the positron have in order to have a non-vanishing interaction? How can you know that? So the hint is the interaction proceeds not in a random way, but the interaction proceeds with a photon, and the photon has spin 1. Photon has spin 1. Therefore, the interaction can only happen if the total spin or angular momentum of the incoming particle is such that we can produce a photon with spin 1. And therefore, if the two angular momenta would add up to exactly 0, we cannot produce a photon and there cannot be an interaction. Said in the opposite way, it means the positron must have such a helicity that the two angular momenta add up to something non-zero. And that means it must have this sort of helicity, so it must be left-handed. Otherwise, there is no interaction. That is helicity equal to -1/2, otherwise no interaction. Okay. So therefore I've already written down here the appropriate spinors for that situation. For example, in the initial state, we have an initial state spinor for an electron with s equal +1/2 and positron with s equal -1/2. And that will give a non-zero result, and you can check yourself as an exercise. If you assume the opposite, then you will just get 0 from the final. Okay, so we know that. And then let us next look at the final state. That is supposed to be the final state here of the process. So we have an outgoing mu plus mu minus. Mu minus here and mu plus there. And then of course the interesting angle is the angle theta between the muon and the original electron. That is the angle theta. And so now what do we expect for the helicities of mu plus mu minus? First of all, they must come from a photon with spin 1. Therefore the same argument is valid also for them. So they must have opposite helicities. They must have opposite helicities. Which ones we don't yet know, but for sure the helicities must be opposite. Otherwise, again, the interaction is 0 and they cannot be produced. So let's say they have some opposite helicities, for example, that one here and that one, but that is now just an example. We don't know yet what helicities they must have, but let us write down some expectations. Let us write down some expectations maybe here. What do we expect? First of all, we expect opposite helicity of mu plus mu minus, otherwise the interaction would be 0. And then let us look at angular momentum now, not only spin but proper angular momentum. Then our initial state is a state where there is the z-axis, so that is supposed to be the z-axis. This is singled out, so everything happens in the z-axis direction. And therefore the particles do not have any orbital angular momentum in the z-axis, but they have spin. So the total angular momentum of the initial state in z direction is exactly the spin. So it's a total angular momentum in z direction of 1. So this initial state is clearly an eigenstate of total angular momentum in z direction with eigenvalue 1. If we look at this final state, then this is, if the angle is not 0, or 180 degrees, then this will not be an eigenstate of angular momentum in z direction, but it might be an eigenstate of angular momentum in another direction, but certainly not in z direction. And therefore we are asking here for the probability amplitude that an eigenstate of Jz becomes a state which is not an eigenstate of Jz. And so, of course, there is some non-vanishing probability, but there we get some expectations. So let's write it down. The initial state has Jz equal plus 1 is an eigenstate. And the final state in general not. And so the overlap, the probability amplitude that Jz eigenstate goes into some other state, like an eigenstate of Jx or Jy, is of course in general non-zero, but it depends on the angle. Clearly there will be some angular dependence. Actually there is an exception, namely for certain angles that is an eigenstate of Jz, namely for theta equals 0 and for theta equal 180 degrees. That is expected to be an eigenstate. So let's write it down, except theta equals 0 or 180 degrees. So we expect that the probability amplitude is some function of theta with a non-trivial theta dependence, which vanishes if the final state has Jz equal minus 1. So under the condition that the final state is also an eigenstate of Jz but with a different eigenvalue, of course the states are orthogonal and the probability vanishes. But in all other cases where the final state is an eigenstate of some other operator but not of Jz, then the probability amplitude could be anything and it will depend on the angle. So these are our expectations, and we can now check the expectations and do the explicit calculation and then understand how the spinors play in order to really produce those properties. So and we can do that quite nicely with our setup. We have set up our process calculation in terms of those, let's say, generalized currents for the electron line and for the muon line, E mu and M mu. And we can now, using the explicit spinors and the explicit situation, write down an explicit value, first of all, for that E mu corresponding to the initial state electron-positron line, which couples to the photon, right? So that was this expression here, just that part of the Feynman diagram, this object. And it is given by E times Q times V bar of particle 2 times gamma mu times U of the particle 1. Now we can plug in explicit expressions for it. So the spinors, they all have the prefactor square root of 2e, therefore we get as a prefactor E times Q times 2e. And then we can plug in the explicit values of the spinors. And we take the non-vanishing situation where we already know what we have written down here, namely the electron is in the S equal plus state and the positron in the S equal minus state. So let us write down the explicit spinors for that. And so we begin with V2 bar. V2 bar is then this here, 0, 0, 0, 1. And the bar means that we have to multiply with gamma 0. Gamma 0, just to remind you, is 0, 1, 1, 0 in our chiral representation. And the gamma I is that 0, sigma I minus sigma I 0. These are the gamma matrices. And okay, so gamma 0 has to be multiplied. That is this block matrix with 2 by 2 blocks. Then we have gamma mu. Gamma mu is then this here. And that is often summarized like this. So the gamma mu is written with sigma mu and sigma bar mu, where sigma mu for spatial indices it's just the Pauli matrix and sigma bar is minus the Pauli matrix. And for mu equals 0, both are just the unit matrix. So this is just a simple to abbreviate both cases uniformly. Then, so this is V2 bar times gamma mu, now times U1. U1 is this 0, 0, 1, 0. Okay, EQ times 2E, then times that just flips the order of the 2 by 2 blocks. So then we get 0, 1, 0, 0 times that. And what is the result of this expression? So we just take the matrix element of that sigma matrix here. We take the matrix element with index 2, 1. So we take EQ times 2E times the sigma mu matrix element 2, 1. Okay? The 2, 1 come from the product of this with the only non-vanishing entry here is in position 2, and here the only non-vanishing entry is in position 1 of that dot matrix. Therefore we get the matrix element 2, 1 of that sigma. So, and that is now a Lorentz vector with a Lorentz index mu. For every mu we have the result. What is our result? So we can write it down explicitly, EQ times 2E, and now here comes a 4 vector with 4 components. What are the 4 components of our 4 vector? So they are the 2, 1 components of the respective Pauli matrix. So here comes the 2, 1 component of the unit matrix. Here comes the 2, 1 component of the sigma 1 matrix, here of the sigma 2 matrix, here of the sigma 3 matrix. So what are the entries? Do it yourselves. So the 2, 1 entries of this sigma mu. Do it yourself such that I see that you understand what we are doing. So some of them are, for example, 0. Wait 5 seconds. Okay. Yep. So 0, 1, I, and 0. Okay. You understand all where it comes from? The explicit entries of the Pauli matrix at position 2, 1. And therefore we get this explicit value. So that is our, let's say, generalized current for the electron-positron line coupling to the photon. It is a Lorentz 4 vector, and so far we never had an explicit form of it, but we used it in computations where it was kind of hidden what it actually is. But now you see for the first time with full details what this EMU actually is for an explicit case with explicit knowledge of the spins of the respective particles. And so that is actually kind of a beautiful form, because have you seen such a 4 vector before in your life? I assume, I hope yes, because that is exactly the polarization vector of electromagnetic wave, which is circularly polarized. This corresponds to a polarization vector of circular polarization of a plane electromagnetic wave in classical electrodynamics, circular polarized in a right-handed way, exactly as it corresponds here to the initial state. So this can be written as a polarization vector of plane electromagnetic wave with circular right-handed polarization. would be epsilon mu is equal to exactly this. So, and our calculation automatically provides us with such a polarization vector, so we can interpret this in a physical way. The physical interpretation is, of course, exactly this, that we have now here half of our process, E plus E minus, goes into a photon, and the helicities of E plus E minus are such that the spins add up to +1, and therefore we produce a photon with spin or helicity +1, and that corresponds to such a plane wave with this circular polarization. Epsilon. So that is a nice physical interpretation. Now we can go on calculating our physical process for E plus E minus to mu plus mu minus, and then this is half of the process, and the other half is that m mu for the muon line, and that will be contracted mu mu with this 4 vector here. Yes? For -1/2 as well. Okay, but by the way, you have to look at the correct table of the spinoscript for the momentum, because the electron has momentum in plus direction, the positron has momentum in the minus direction. And there is another table in the spinoscript where there is the momentum Q bar, as it is called there, and that is the thing that you need to use for the positrons, the opposite momentum. And I've used that here already, so I didn't write down the momentum arguments, but very clearly the momentum of the positron is different from the momentum of the electron, and the spinos depend on the momentum and the spin, and this is all taken into account here in this table. So I did the work in appropriately reading off from the tables. Okay, now let us go to the muon line. For the muon line, the following is relevant. Namely, ultimately we need to do that contraction E mu times m mu. So that is what comes out if we plug in the propagator, which contains the metric tensor. So ultimately simply those two are contracted, and that is now proportional to that polarization vector epsilon mu times m mu, because the E mu is essentially given by a prefactor times this polarization vector epsilon mu. And so it's useful now to study for us, first of all, only the contraction with the polarization vector of the photon. And that of course corresponds to asking, you have a photon which is circularly polarized with spin equal +1 in z direction. What is the probability to produce mu plus mu minus out of this photon, where the mu plus mu minus fly in a certain direction with angle theta? That is the question, and the essential answer comes from evaluating this product here. So let us do that. Let us evaluate this product. M epsilon mu, or epsilon, let's put lower index mu, times m mu. Then, that is epsilon. So what do we get? You have to watch out that we have a lower index now, so we get a minus here in front of the spatial components, and so we get -1 times m with index 1 minus I times m with index 2. That is what we get. And so from the muon line, only those two components are actually relevant. Let's work it out a little bit further. So So the muon has the similar structure as this one with E times Q times the spinors. And so here we have now minus E times Q. Then we have the spinors. We have U3 bar for the outgoing mu minus. And then we have here in between gamma matrices, and then we have V4 for the outgoing mu plus. And in between, we now have gamma matrices, but we have specifically the combination gamma 1 matrix plus I times gamma 2 matrix. That is what we have. So we can ask, what is actually the value of this combination of gamma matrices, gamma 1 plus I times gamma 2? And what is relevant there is the combination of the Pauli matrices sigma 1 plus I times sigma 2, because the gamma matrices are composed of the Pauli matrices, and so you need to know what is the sum of those two. And okay, so in the Pauli matrix sigma 2 you have minus I plus I here. In sigma 1 you have 1, 1. So the sum is simply this. You have here a 2, and everywhere else we have a 0. That is the sum of those two Pauli matrices. And so you can plug that into the gamma matrix. And so here in this in between, you have a very specific 4x4 matrix where almost all entries are 0, except that one entry is 2 here in the upper block, and in the lower block one entry is minus 2. That's all. Everything else is 0. And so then that means you contract the two spinors with that matrix, which consists essentially of zeros, and two entries are plus minus 2. So and then this can be of course also explicitly evaluated. So and I think let me remove the blackboard and let's evaluate it explicitly for the two cases of the two different spins. What are we going to do? We evaluate exactly this expression here, explicitly plugging in the result for the muon spinors U3 and V4, which I deleted. So this V4 is probably that, and then 0, 0, minus S plus C. The arguments are always the same. Square root 2E minus C minus S 0, 0. Okay. So case 1, mu minus has spin plus 1, and mu plus has helicity minus 1. So that is the case which is very closely related to the initial state, where also the electron has plus 1/2, positron has minus 1/2. So it's basically the spin is the same as in the initial state, only the angle is maybe changed. And then we have to use the upper line here for our spinors. So let's plug it in. Then our epsilon mu times m mu becomes the following: minus dq times 2 times the energy. And then our spinor here is this 0, 0, cs, and c and s always are cosine and sine of theta half. That, and then we have this block matrix here, 0 block, and here the block 0, 2, 2, 0, and here the block 0, minus 2, 2, 0, and everywhere else 0. And then we have the other spinor, U bar. And of course the bar always flips CS 0, 0. That is the meaning of the bar, where we multiply with gamma 0, which just exchanges the two blocks. Then V4, 0, 0, minus S, C. Okay, what's the result? The result, only the upper block matters. The upper block is projected out, because here we only have the lower block. So this block is multiplied with that upper block, and also this. So the only non-vanishing term comes from cosine hitting the 2, and then the 2 hits the other cosine. So we get 2 times cosine square from this expression, which, let us write it like this, EQ 2e times 2 times cosine square of theta half. And the other case, mu minus with minus 1/2 and mu plus with plus 1/2. So there we get epsilon mu times mu is equal to minus EQ times 2e. Then times the opposite spinos. So here we have the opposite, 0, 0, minus S and C. So I already reversed the 2 blocks. Then our matrix and so on. And here we have this block here, which is the only non-vanishing thing. And the other spinor is that one with minus C minus S 0, 0. Okay, now the only non-vanishing term comes when that block hits the lower block here. The minus sign hits the minus 2, and then it hits the other minus sign. That gives in total minus 2 times sine square. So minus E Q 2e, then times minus 2 sine square of theta half. So that is our angular dependence. What is actually cosine square theta over 2? That is the same as 1 plus cosine theta without 1 over 2. And this here is the same as the opposite, namely cosine theta minus 1. And so we see now that indeed our amplitudes, our probability amplitudes, already before squaring produce the angular dependence that we were expecting from our intuition. Yesterday we only obtained the angular dependence after spin summation and after squaring the amplitude, because only then we were able to use this Casimir trick and to explicitly evaluate the expression in terms of angles. But here we are now already able to evaluate the expression at the amplitude level before squaring. So we have a much more detailed information than yesterday, but the angular dependence is exactly what we expected. Let us explain. At the first case, where the mu minus keeps the helicity of the original E minus, basically for theta being 0, the particles just continue to move along in their original direction and the spin is completely conserved. So for theta equals 0, that final state is an eigenstate of JC with the same eigenvalue as the initial state. And so therefore for theta equals 0, we here have the maximum amplitude. This is maximized for theta equals 0. Perfectly in line with angular momentum conservation. However, if the angle is 180 degrees, that probability or amplitude goes to 0. Because for theta equal 180 degrees, this becomes an eigenstate of JC with the opposite eigenvalue, and therefore there cannot be the probability amplitude to create that final state. So this is completely reproduced in line with our expectation. And here it's the opposite. It's also in line with our expectation, because here the mu minus has the opposite helicity as the original E minus. Therefore, if the theta angle is 0, the spin would not be conserved, and angular momentum would change from +1 to -1, which cannot happen. Therefore, for theta equals 0, that becomes 0. However, for theta equal 180 degrees, it means that now the mu plus carries forward the original spin of the electron. So the angular momentum is conserved, and therefore for theta equal 180 degrees, we get here the maximum amplitude, which is in particular non-zero. So it's all in line with expectation from spin conservation and angular momentum conservation. And okay, so let's write it down, TFI for all these cases. E minus with 1/2, E plus minus 1/2, going into mu minus with 1/2, or mu plus with minus 1/2, or the opposite, let's say plus minus minus plus. This amplitude is now the following, namely we have always the prefactor minus EQ times 2E, and then we have the two possibilities, either 1 plus cosine theta or cosine theta minus 1. And let me write down in words, it agrees fully with the expectation. So we have understood at a detailed level of spin and angular momentum where the theta dependence comes from, and we understand that we can actually explicitly evaluate such processes using explicit spin rules. Ah, yes, right. Okay, so I forgot some factors because that is only this thing here, and of course, let's say proportional. So EQ and also 2E becomes square, and then there is still a term, a factor from the propagator. So let's simply write proportional to, and the proportionality factor would be 1/q to the second 1/q squared. Yes. So okay, actually, we can do it explicitly. It's exactly divided by q squared, and it's fully correct and equal. So this agrees with our angular momentum discussion, but it also agrees with yesterday's result, where we had the sum over all the spins of the squared matrix elements. The sum over all the spins of the squared matrix elements, if we do this now, then we square each one and add them up, then we get 1 plus cosine square, 1 minus cosine square. The mixed term cancels, and we get 2 plus 2 times cosine square, and that is exactly what we found yesterday. So we have also full agreement with yesterday's result, which was obtained using a completely different method, and this is what I wanted to show you, that you have indeed both ways to do calculations, and you can work at the level of the amplitude with explicit spinors and get some detailed understanding, but you can also do the spin summation where you don't care anymore about such details, but obtain the result for the squared amplitude and therefore for the probability. So that is nice to know, and of course, depending on the situation, both procedures are obviously useful. That ends our discussion of E plus E minus to mu plus mu minus, and we would now move on to a different physics process. And in the lecture of the next process, I would most likely not discuss these explicit spinors, but it can happen with a quite high likelihood that you are supposed to calculate with explicit spinors that process in the exercise. So therefore, we will practice this once more. Okay, next topic. Compton scattering. Yet another one of the classical QED processes where one can discuss a lot, both in physics and in quantum field theory. Compton scattering is the process E minus gamma to E minus gamma. So it's a process where we do not involve antiparticles. It's only electrons and photons. Therefore, it is a process that happens even in classical physics, which one can even discuss in classical electrodynamics without knowing anything about quantum mechanics or even quantum field theory. And actually, I want to start with a brief review of your classical electrodynamics discussions. Classical electrodynamics, but last time I checked, it's not always taught in classical electrodynamics lectures. For example, I didn't do it myself, and also this semester in the electrodynamics it wasn't taught, but anyway, it's a topic of classical electrodynamics, namely the so-called Thomson scattering. And you know enough in order to immediately understand what happens. Namely, you take a charged particle. Think of classical electrodynamics. You have charged particles like electrons, but they are treated now as classical objects with no quantum mechanics. You have a point charge. And here you have a light wave. Let's say a plane wave. And you shine a plane light wave onto your charge with a certain frequency. It's a homogeneous plane light wave constantly shining onto the charge. Then the charge experiences an oscillating electric field. Because of the oscillating electric field, the charge moves up and down, accelerated by the field. And since the field oscillates, positive and negative, the charge of course will do an oscillatory motion with the same frequency as the original light wave. So if the light wave looks like this, then the electric field is perpendicular to the wave. It could go either in the direction of the blackboard or perpendicular to the blackboard. So there are different polarizations possible for the light wave. But the charge will oscillate in the direction of the electric field. So let's assume it oscillates in this direction. Anyway, orthogonal to the light direction. And so now you have an accelerated charge. If you have an accelerated charge in classical electrodynamics, the charge will radiate. It will radiate an electromagnetic wave. And actually this, let's say it does a harmonic oscillator motion. So this is an antenna, which is, I think it's also sometimes called Hertz dipole radiation. It's simply an antenna. An antenna is something where charge moves up and down. And then the antenna radiates electromagnetic waves in all directions. It radiates in all directions, but of course not in all directions equally. For example, an antenna cannot radiate anything in the direction of the antenna. It can only radiate in all other directions. Actually, it's of course somehow cosine square or sine square of the angle relative to the antenna. So you have an emission of light. And let's say the light wave has a frequency omega, and the emitted light has the same frequency omega as well, because of course everything here is a harmonic motion with the same frequency omega. Therefore everything oscillates with the same frequency omega, also the emitted light. Now what is the intensity? Let us look at the two situations of the polarization of the light individually. So if the electric field of the incoming light wave is oriented like this one here, so that everything happens in the blackboard plane, so the field is in the blackboard plane and then the radiation is also considered in the plane of the blackboard, then the angular dependence is as follows, namely in the direction of the antenna there is nothing, in orthogonal direction the emission is maximal. So, and if we have this angle theta here, then the intensity is proportional to cosine square of the angle theta. Okay. However, in the opposite case, where the polarization is orthogonal to the blackboard, but we still consider radiation in the blackboard direction, but the charge now moves in this direction, then of course all directions in the blackboard are equally likely, equally intense. So the intensity is simply proportional to unity, so there is no angular dependence of the intensity. And if you do not care about the polarization of the incoming light, in other words, the light is unpolarized and each polarization is equally likely, then what counts is the average, and the average intensity is then given by 1 plus cosine squared theta. So and that is then the so-called Thomson cross-section, which can be written also in classical electrodynamics as d sigma by d omega, is the Thomson cross-section, which has the following prefactor. If you calculate it, eq to the 4th power divided by 32 pi square times m square, where m is the mass of the charged particle, and then comes the angular dependence 1 plus cosine square theta. And you cannot understand the prefactor, that must come from a calculation, but you can understand the angular dependence. That is Thomson scattering. Maybe you have, for sure you did radiation of accelerated charges with Liénard-Wiechert potentials and so on. Maybe you also discussed Rayleigh scattering, which is responsible for the blue sky and so on. Rayleigh scattering is basically the same as Thomson scattering, with the difference that the charge is not free and cannot freely accelerate from the electric field, but the charge is bound in a molecule or atom, and therefore there is a harmonic oscillator force acting onto the charge in addition to the electric field. And then in the case where you have this harmonic oscillator force on the charge from inside of the atom, low frequencies are disfavored because it's very difficult for an electric field to move away for a long time the charge from its center. But high frequencies are easy to obtain, and therefore you get this omega to the 4 rise of the cross-section in the case of Rayleigh scattering, and therefore the sky is blue and not red. But for Thomson scattering, we consider a free charge, and then we get this intensity from classical electrodynamics. Okay, now what is in contrast to this Compton scattering? Compton scattering is first of all the same, however generalized, so that we also allow high energies, and of course we take into account quantum effects. Anyway, even if we do not know about quantum effects, we can simply measure this process experimentally, and that has of course been done. And what was discovered? It was discovered that it does not work that way. It doesn't. It works only approximately like this for very low frequencies. However, at certain high frequencies of the light, you suddenly discover that actually the frequency of the light wave is changed. The frequency of the outcoming light is not the same as the frequency of the incoming light. And how can you possibly understand that? You can of course understand it by knowing that a light wave consists of photons. The photons behave like particles. Particles hit another particle like the charge. Then you have momentum conservation. The momentum is proportional to the frequency. Since the momentum of the photon changes, the frequency changes as well. So that is an explanation of Compton scattering. And so by measuring it, you prove experimentally that the photon is actually a particle with momentum h bar k, of course, which is the same as h bar omega in magnitude, and we have momentum conservation. Namely, the process now looks like this. We have here a photon. Here we have a charged particle. First, the photon has momentum k. The charged particle has momentum p. Afterwards, the photon has momentum k prime, and the particle moves here with momentum p prime, and we have four-dimensional momentum conservation k mu plus p mu equal k prime mu plus p prime mu. And from that, of course, we get the frequency shift. That is the proof that the photons are actually not completely described by classical electrodynamics, but by quantum field theory, and that the photon is a particle. Okay, so you know that, of course, that there exists this frequency shift, and you can trivially calculate it from kinematics. And for sure you have done it many years ago, maybe already at school. But now we have QED, and that means we can find a unified description of all of this within QED. QED must, of course, contain classical electrodynamics as a limit. And of course, it is the correct theory to describe that process. And therefore, what we are now going to do is to describe the process within QED. We will look at the process at high energies, where the frequency change is important. But we will also look at the low energy limit, where we should recover maybe the classical result or maybe plus corrections. So anyway, that is our goal now, to find such a unified description in QED. So now we are hopefully motivated, and let us look at the process in QED, and for that we need to start in the same order as for the previous process. We first look at the T matrix element. In other words, at the probability amplitude for the process happening. And so we are now considering concretely this process, photon and electron going into another photon and electron with modified momenta. And for this, there are two Feynman diagrams. We already had them in our derivation of Feynman rules, and the diagrams look like this. That is one diagram, and the other diagram looks like that, where the photons are exchanged. And so let's write down all the details. So here we have incoming the photon momentum k and the electron momentum p, and the arrow goes like this. And here we have outgoing the momentum k prime and outgoing momentum p prime. Here we have the same, incoming momentum p and incoming momentum k, outgoing momentum k prime and outgoing momentum p prime. Then we have a propagator, an internal line, and the momentum on the internal line is given by momentum conservation. And so here let us call the internal momentum QA, so that is diagram A, and the other one is diagram B. And here the internal momentum is the sum of the two here, P plus K. But of course it's also the same as P prime plus K prime. In the other diagram, the internal momentum is different. Let's call it QB. And what is it? By momentum conservation, so here in this line along the arrow, there flows a momentum P minus K prime, because K prime is carried away. P minus K prime. But we can also look at the other vertex, so this QB is also equal to P prime minus K. It's also equal. Okay, and with this information we can write down the Feynman rules for this process. So we have I times TFI for diagram A and I times TFI for diagram B. What are the Feynman rules? The Feynman rules for both diagrams are obtained again by taking the fermion line and going against the arrow direction and writing down all the spinor objects corresponding to all the Feynman rules. So here that means we have a long fermion line. We have to start here, and then we start with a spinor corresponding to the outgoing electron, and after a while we write down the spinor for the incoming electron. Okay, so we start with that spinor, which is u prime, let's call it u prime bar. And then we have here the vertex, minus I eq gamma mu. Let's call the index for the outgoing photon, let's call it mu. And the index for the incoming photon we call mu. Then next we have here the line for the propagator, which is I times qa slash plus m divided by qa square minus m square. That is the propagator Feynman rule. Then we have the vertex on the left, minus I eq gamma mu now. And finally we have the spinor for the incoming electron, which we call simply u. We drop the arguments and we differentiate u and u prime. We are not done. We also have the Feynman rules for the photons. The photons get Feynman rules for polarization vectors, epsilon mu. So the incoming photon has a Feynman rule epsilon mu for the incoming photon, and the outgoing has epsilon prime star mu. The star is because the outgoing photons always get a star in the polarization vector, and the prime simply denotes which photon we are talking about, instead of writing down the arguments. So I mean, just to avoid confusion, epsilon prime mu is epsilon mu of k prime and lambda. But I will not write this explicit for. So for the second amplitude, we have the same u bar prime, and then we have here the opposite vertex, namely for the incoming photon. So we have minus I eq gamma mu now. We have in the internal propagator qb slash plus m divided by qb square minus m square minus I eq gamma mu, then u, and then the same epsilon mu and epsilon prime star mu. So, and one could now simplify a little bit and, for example, collect the factors of I and minus 1 and so on, and collect the factors of E times Q, as we did before, and we will do that when we calculate the process explicitly, but let us look a little bit at some structural properties of the amplitude. What are the questions? Yeah, so I always choose to label the incoming photon with an index mu, and the incoming photon couples to that vertex here, which is first, and therefore here we have the index mu. The name of the index doesn't matter, but what matters is that this epsilon is contracted to that gamma, and vice versa. Other questions? Okay, 2 or 3. Let us look at the structural property before doing a couple of reflex and just plugging in expressions, squaring and everything and calculating traces. So there is something called Watt identity, and let us prove that Watt identity of the process. So let us write, first of all, this TFI in total, A plus B. Let's write it in the following way: M mu nu times epsilon mu epsilon prime star nu. So obviously this curly M mu nu simply summarizes everything here without the epsilons. It summarizes everything without the epsilons. So we have an abbreviation for the object here without the epsilons, and that object has two open indices, mu nu, otherwise it is a number. all the spinors are saturated, so it's a number with two open indices mu nu. Let us look at the properties of that m mu nu. I claim that we have the following: k mu m mu nu and k prime nu m mu nu is 0. That means, simply put, you take the polarization vector of the photon and you replace it by the corresponding momentum of the photon, and then you get 0. So here epsilon is multiplied normally with m mu nu. We replace epsilon by k, and then we get 0. And here we replace epsilon prime nu by k prime nu, and we also get 0. So this is a so-called Watt identity. There are many such identities, and they all collectively are called Watt identities, and this is one example of such a Watt identity, and here we have this relationship. Let us prove this identity. And the proof I am going to show you is a very typical proof that you can apply not only here, but also in many, many other similar cases. So the method is very important to realize and understand. It's a very simple method. Namely, we write down k mu m mu nu, and in this k mu m mu nu, what happens? Of course, we only look at one of the two cases. So k mu m mu nu, what happens? The k mu is now contracted with that expression, so the k mu hits the gamma mu here. It hits the gamma mu here, so we get from the gamma mu, we get k slash. So we get k slash here, and in the other case we get k slash there. What can we do with this k slash? So we get k mu gamma mu is equal to k slash, and the Watt identity derivation trick is the following, namely you replace the k slash by a difference of the adjacent momenta. So for example, actually here in the first case, gamma mu, the gamma mu in the diagram, it sits here. So you get basically a k slash at this position in the diagram. At this position in the diagram, we have here momentum k incoming. Here we have qa outgoing and p incoming. So we can replace the k by the difference of qa minus p. And that is what we are going to do. So we replace in the first diagram k by qa slash minus p, which is the same thing. And actually we do even more. We replace it by qa slash minus m minus p slash minus m. That is what we do. And then we see what happens. In the other diagram, the k slash appears at this point. Here enters k slash in the second diagram. And so here our strategy is to replace k by p prime minus qb, which is also true. K is p prime minus qb. So we replace it by p prime minus qb. And again, we do the same. We even do more. P prime slash minus m minus qb slash minus m. That's what we do. What happens if we do that? Insert in diagram A. So what happens if we insert exactly this idea into diagram A? So we insert this expression as k mu at this point. So now at this point there stands this combination here. So maybe I should write it down. So we get u, so what are all the prefactors? All the prefactors, they boil down to minus IEQ. So this minus IEQ is factored out, and then we get u prime bar times minus IEQ gamma nu times IQA slash plus m divided QA square minus m square. And here we have u. And now in between we plug in this expression. So here comes now that expression. QA slash minus m minus p slash minus m. Once I'm explicit, but now you should look at the blackboard to see what happens, because now a big simplification appears. The p slash minus m hits the u. What happens if p slash minus m hits the u? U is a spinor which satisfies the Dirac equation. That is 0. P slash u equal mu. That is the definition of u. So therefore that gives 0. This simplifies if we connect it to that propagator here to its left. So q slash minus m times q slash plus m gives q square minus m square divided by q square minus m square gives 1. So that times this gives 1 up to the I. So the whole thing simplifies for I. That is the simplification that always happens if you do something like this. And so what happens in B? In B, we get also a prefactor minus I eq, then q prime bar, and then the same thing happens on the left. And maybe we can do it directly without writing it down explicitly. Here we plug in the other expression. Then the p slash minus m stands here. P slash minus m stands here. That also gives 0 because it hits the u prime. So p slash minus m gives 0, and then we have minus qb minus m. That hits that propagator. It combines to 1, but there is a minus in front. So that whole thing gives minus I. So we get times minus I from the whole thing, and then what remains is minus I eq gamma nu u. And so now you see the two terms are equal up to the minus sign. So everything which differed between the two lines A and B has dropped out, and the complicated thing here becomes I, the complicated thing there becomes minus I, and everything else is exactly identical. Therefore the sum is 0. And therefore the what identity is proven. Okay, that is the trick that you need to use for proving such what identities, namely to replace the momenta that you contract with by the differences of the two adjacent momenta, and then you will always be able to do such simplifications. This works for all final diagrams, also for much more complicated ones. So and then we can use that what identity, so we know structurally that our m mu nu has this simple property, and that is important for the physics interpretation, as we will discuss next week also. But it is also important for the technical procedure of the next steps in our calculation. So I think we have time to do exactly the next step in our analysis, which uses the what identity. First, do you have a question to this derivation here? Does it look clear enough? So we will again look at the unpolarized case, and the last time we did unpolarized fermions, which gave rise to traces and Casimir's trick. Now we want to begin with unpolarized photons, because obviously that is the new element which we should discuss here. And for that discussion we need the what identity. So let us write down the square, TFI square, is now our m mu nu times m star mu prime times epsilon mu epsilon star mu prime epsilon prime star nu epsilon prime without star nu prime. That is the square of our TFI matrix element, where I already used the simple notation with this curly m mu nu and explicitly highlighting the role of the photon polarization vectors. And so those vectors now depend on the photon spin or the photon polarization, and we might want to sum over all possibilities of the photon spin for the incoming photon and over all possible spins of the outgoing photon. And then we need to see what happens. And so now let us come back to the discussion of polarization vectors. Maybe you remember that that was an extremely long and complicated chapter in our lecture to discuss polarization vectors of massive and massless spin 1 particles, and now we come back. So let us memorize that there are physical polarization vectors which correspond to lambda equal 1 and 2, and they are simply epsilon mu for lambda equal 1 and 2. But there are also unphysical polarization vectors, and they are the ones for lambda equal 0 and the one for lambda equal 3. And we had two different bases, one with L and S and one with 0 and 3. Let us now use the one with 0 and 3 for a reason I will explain. But anyway, the two satisfy a relationship. Namely, if I add them, I get something simple. Namely, if I add them, this had a 1 in the 0 component, and this was just a spatial momentum in the spatial components, but a 0 in the 0 component. If I sum the two, then I get exactly the momentum 4 vector of the corresponding photon up to a normalization. So the sum is k mu divided by the energy k0. That was exactly the definition of these two polarization vectors. And then I told you that, okay, it's a drawback of that basis that none of the polarization vectors alone is equal to the momentum. So, but this linear combination actually is equal to the momentum up to normalization. So now we look at the behavior of these unphysical polarizations resulting from the word identity which we have just proven. What does the word identity tell us about the behavior of the unphysical polarizations? It tells us the following. If you do m mu nu times epsilon with lambda equals 0 and compare it to m mu nu times epsilon mu with lambda equals 3, then there is a relation. What relation? Namely, m times k is 0. The sum of the two gives k. Therefore, if I add the two, we get 0. In other words, one is the negative of the other one. So that is extremely important, and that allows us then in the final discussion to remove the unphysical polarizations from our discussion in a very transparent way. So that is first of all a relationship. For an individual photon, and now we have two photons in our theory, therefore, is there a problem? Time's up. Okay, about me. Good. Anyway, here we have a minus, and we have two photons. Therefore, we can now write the analogous relationship, namely m mu nu times epsilon mu with 3 epsilon, so m star mu prime, m star mu prime, m mu nu times epsilon mu and epsilon mu prime star for one photon but squared, 3 polarization, and we compare it to the same expression with the 0 polarization. then they are equal because the sign drops out. So if we do the square, then the sign drops out. So we have simply squared the previous expression. Now, that means that if we do a polarization sum, the unphysical polarizations drop out. So let's make that explicit. We have first of all the sum of lambda equal 1 and 2 of this expression m star mu prime m mu of epsilon mu epsilon star mu prime. And it's sufficient to do it only for one photon, and for the other one it works in the same way. That is the same as if we draw the sum of lambda from 0 to 3 of the same expression. Okay. So if we sum from 1 to 3, then the 0 and 3 component, they are the same. What happened? Okay, and of course I should multiply with this, so not here but here, with this g lambda lambda, this norm that we always had in the summation of the polarization vectors. G lambda lambda means that we sum over the g lambda lambda. We sum with the correct sign. So lambda 3 appears with a negative sign, lambda 0 appears with a positive sign, and then because of that sign, the two cancel here because they are equal, and that means in this sum we can sum from 1 to 3 or from 1 to 2, and the result is the same. What we want from physics is we want only physical polarization, so that is what we want, and that gives us the physical result of our process for the two physical spin orientations of the photon. However, alternatively, we can instead calculate this summation over lambda from 0 to 3 with this sign-depending normalization. The result is the same. And the right-hand side is much easier because now we have a completeness relation. Namely, the completeness relation is sum over lambda from 0 to 3 with this sign-dependent prefactor of that epsilon mu epsilon prime star mu prime is equal to minus the metric tensor g mu mu prime. That is what we established at the time. And so this summation over all four basis polarization vectors just gives, because they are a complete basis of four-dimensional space, gives the metric tensor. And so therefore here on the right hand side we can plug in the metric tensor times minus 1 as the polarization sum over the epsilon. And that is of course a very simple result. So we can replace after spin summation the epsilons by simply a metric tensor. That is it. And the Ward identity tells us that this replacement is actually even correct if we are only interested in the physical polarizations. Even though for the physical polarizations, of course, that relationship here is not, but it becomes effectively valid if we contract it with such a physical finite matrix element. So therefore we have the effective rule that we can replace the polarization sum of epsilon 1 and 2 of epsilon prime star by a metric tensor g mu mu prime to check. So this is here, sorry, this is plus and that is minus. Sorry about the confusion of signs in physical matrix elements. Okay. So even though the last line is not an equality, it becomes an equality once you contract it with such a physical matrix element. This is the outcome of this discussion. And just in order to connect it a little bit more to our discussion at the time where we had physical, unphysical states, and we discussed a lot the relationship between Lorentz invariance, physical degrees of freedom, and also gauge invariance. You see here that the polarization vectors for the physical degrees of freedom, they are of course not Lorentz covariant 4 vectors. So from their Lorentz transformation properties alone, it is not obvious that a combination like this is Lorentz invariant actually. But because of that replacement, it becomes now obvious that the whole relationship here, at least the squared matrix element, becomes Lorentz invariant. And so you see again that gauge invariance and this current conservation expressed by the Watt identity is responsible for the validity of Lorentz invariance of our physical calculations. Okay, so do we have anything else? Let me maybe just write the final result, which we can then work with the next time. The final result is, of course, that the spin-summed matrix element sum over lambda and lambda prime for the two photons TFI square is given by this m mu nu, m star mu prime times metric tensor g mu prime times g mu prime. So that is what I meant. It is obviously Lorentz invariant, because every element in this expression is Lorentz covariant. And that is what we can evaluate the next time. Next time we will then also do the summation over the fermion spins, which gives traces, and then we can obtain the final result for the squared amplitude and the probability for this process. And we can look at the limits, classical electrodynamics, and ionometry. Okay, so see you then on Thursday for the exercise.